Alright, so at the end of the last lesson I had a link to a Mythbusters video where they talked about the shot bullet versus drop bullet. And what that video would really show you is that motion in the x direction or horizontal direction is independent of motion in the y direction or vertical direction. Basically, that horizontal motion does not have any impact on vertical motion and vice versa. If you're moving side to side, the amount of time that bullet stayed in the air is the same. So for our previous problem when we talked about Michael Jordan, it wouldn't matter if Michael Jordan is running at the basket. If he stays in the air for 2 seconds, he has to jump 16 feet into the air. Ultimately, while this may sound like it doesn't make our life any easier, this will make our life easier because it means that I have now a technique to deal with two-dimensional problems, or problems where something is moving in more than one direction. A good example of a two-dimensional problem, here I have a spacecraft and it's moving in the x and the y direction. It's both moving to the right and moving up, and the velocities are changing. And so it's moving along this arc path rather than a straight line path. So we could actually use this idea of independence of motion to begin to predict what's going to happen to the motion of the spacecraft. So let's do a spacecraft problem and say that it's moving in an initial direction in the x direction, or initial velocity in the x direction of 22 meters per second, and has an acceleration of 24 meters per second squared. And in the y direction, it's moving at an initial velocity of 14 meters per second and an acceleration of 12 meters per second squared. After 7 seconds, what is the displacement of the spaceship? Basically, how far has the spaceship traveled from where it started during those 7 seconds, and in what direction did it travel? So what I do with this type of problem with multiple directions, with 2 or more directions of things going on, is I start to break up my known quantities in what's happening in the x direction and what's happening in the y direction, and separate them. Independence of motion means that I can do a problem on the x direction that's independent of a problem or set of equations on the y direction. One variable which I would consider to be a shared variable in this case is time, but in each of these directions we're going to look at what happens after 7 seconds. Our unknown quantities are the distance x, how far horizontally did this spaceship travel, and y, how far vertically did this spaceship travel. So in either one of these cases, I can use my kinematics formula. Displacement is equal to initial velocity times time plus half acceleration times time. I don't need to do any algebra because those equations are already solved for the variables that I want to use. The one thing to note is that in the second equation here, all that I've done is replace all the x's with y. Y is still a measure of displacement. How far traveled is just a measure of vertical displacement versus horizontal displacement. So if we calculate out what x and y are, what this says is during these 7 seconds, the spaceship moved horizontally 742 meters and vertically 392 meters. If we wanted to figure out the actual displacement of the spaceship, what I'm going to need to do is figure out what is the magnitude of that displacement. It's moved 839 meters, and I'd also want to figure out what is the direction that it's traveled. I'm measuring theta with respect to the positive x-axis, so this angle here is theta. So theta is equal to tangent inverse of y over x. Tangent inverse of 392 over 742 gives you 27.8 degrees. So the final displacement is 839 meters at an angle of 27.8 degrees above the positive x-axis. So that gives us a quick overview of some two-dimensional problems. What we'll look at in the next section is a special type of two-dimensional problem called projectile motion, where the acceleration is just due to gravity.